Hi guys, so this short video is really to recap some of the concepts of magnets and their associated fields that you would have definitely learnt about during the Year 9 Science program. And we're going to extend that a little bit as well. So we're going to talk about the fields around a single magnet, individual magnets reacting to each other's magnetic fields, as well as having a quick look at the magnetic field that's associated with the piece of wire that's carrying current. And we can use all this together to really try to get an explanation for the project that you've been given. So as you might recall, magnetic fields are by definition defined as going from north to south. So the arrows are actually really important because once we have an idea of the direction, we can predict how those magnetic field lines will interact with each other to produce a magnetic force. What you might notice is as you get closer to a magnet, the magnetic field lines get closer together. So we call this a region of high flux density. Where there's a region of high flux density, the magnetic field is stronger and therefore it can exert a greater influence on its surroundings. Now here is the old iron filings experiment. We used to sprinkle them directly onto magnets, but then the magnets got very covered in iron filings. Now we have those little plastic containers with paraffin in them with iron filings that we've used in class. So what happens is the iron filings end up becoming slightly magnetised themselves because they are magnetic and they attract each other, forming clumps. But what it ends up doing for us is really giving us an indication of the direction of the magnetic field and the intensity of the magnetic field around a magnet. As you can see here, those lines are so close to each other, they're almost on top of each other, and that makes sense because we're closer to the pole of the magnet. Of course, they're clumps of iron filings, so there is no direction indicated. But as I said previously, by definition, we assume that magnetic field lines go from north to south. Now, of course, it's important to remember that magnetic fields are in fact three-dimensional. We have this horrible habit in schools of just drawing on a two-dimensional whiteboard, or indeed a two-dimensional iPad, and not really getting a feel for what is in fact in 3D. So we have one of these gadgets at school, and we'll have a bit of a play with that in class, and you can drop a magnet through the middle of that three-dimensional cube, and then that three-dimensional cube is full of iron filings floating in paraffin, and they in fact line up as a three-dimensional magnetic field. If we want to visualize those magnetic field lines as flux lines, this is about the best picture I could find on the internet, and it's a lot better than anything I could draw, but it would look something like that. A little bit overwhelming, but yeah, it's absolutely so important to remember that we live in a 3D world. So what we have here is a simple simulation to show what you'd see if we had a lot of little plotting compasses. We've done something like this at school, but if you had a lot of them, what a compass does is it aligns itself along magnetic field lines. I mean, I can move that magnet and those compasses are going to move a little bit, but if we were to just pick up a pen and draw a line through the overall direction that these compasses are pointing in, we are actually going to produce magnetic field lines as well. Now what I want, so if you could do this with one compass, put it in one spot, put a dot where the north is, move it, put another dot, and join them all up. But having this many magnets would be very cool. Now, what you might have noticed is that, let's have a look at this magnet here. The red end of the magnet is north, but the compass is north. And my goodness, it seems to point south. And that makes sense. What that little needle in the compass is a magnet on a pivot. The north end of that compass needle is the north end of the magnet inside the compass. So believe it or not, compasses point south. I know what you're thinking. Hang on, we've gone orienteering and my compass always points north. Well, you might be surprised to hear that if we were to imagine this to be the magnet inside the Earth's core, it is in fact arranged like that. The north end of the Earth's magnetic field is in fact at the geographic south. And what a compass does is simply aligns itself along those magnetic field lines, therefore pointing to what we call geographic north, but it is in fact the south end of the Earth's internal magnet. What you might notice too is that these field lines are only parallel to the Earth at the equator, and in fact at the extreme North Pole a compass would in fact point vertically. So you'd have to rotate it around in your hand, but it would absolutely point vertically. Okay, so this little simulation shows something we're very familiar with, the attraction between two magnets. If I move this magnet closer to the right magnet, you'll notice the lines between the magnets get closer together, implying a stronger magnetic field. They get further apart, the lines between them get further apart, implying a weaker magnetic field and therefore a weaker force of attraction. The magnetic field lines' directions are not shown here, but recall, we always, by convention, draw them from north to south. All right. Now, so I can move them together, move them apart, and if these were real magnets, you'd really feel them come together and then just snap together, just like they would in class. Yeah? So I'm going to rub out those little squiggles and do something funky here. I'm going to get this magnet and rotate it. So now I've got a north against a north, and what you'll see is these flux lines are pushing away from each other. They're not joining, they're pushing away. And yes, as discussed earlier, this is a region of high flux density and it causes repulsion. Yeah? So if these were real magnets, I can feel that force push them together, especially if they're like super magnets. Pow! Move away from each other. All right, so another good demonstration of how magnetic flux density affects magnetic force. All right, now this simulation is depicting what happens around a conductor when there's a current passing through it. Now, every single piece of wire that's carrying current has a magnetic field around it. And the link between electricity and magnetism is electromagnetism, and that was really first developed by Faraday, and he made a lot of great contributions. If I switch that current off, you'll notice here that those iron filings are not clumping at all. Okay. Now if I was to simply turn that current on a bit, now notice the bigger the current, now notice I'm getting more batteries over here. The bigger the current, the more aligned those iron filing lines are. And if you look over on this side, the thickness of those green arrows is representing the magnitude of the magnetic field produced. So if I was to really increase that, see they get quite fat, those arrows. If I drop this away, they become quite small. And we'll cover in class or on a future video the mathematical formula to work out the magnetic field strength at a certain distance from a conductor, so we can work out the size of the force that may be experienced when that interacts with another magnetic field. All right, now let's think about how we can predict the direction of that field. There's a really good trick, and that is if we align our thumb in the direction of the current, our fingers curl in the direction of the magnetic field. So I'm just going to superimpose that on there. There we go. So if our thumb points along the current, our fingers curl in the direction of the field. Okay, so that's all for this little video presentation. We will discuss these concepts tomorrow, and absolutely we feel free to ask me any questions in class. See you tomorrow.